Okay, off we go. So here's what we were talking about last time. So the big idea. Now we did skip the sort of initial development of this, but I think the believable and what you're gonna the intuitive part of what you need is perfectly visible in what we have right here. When you parameterize a surface, for example, here I'm representing a parameterization of the sphere. Well, as you move in one of the parameter directions, so for example, as I move in the phi direction, well, then I'm going to be moving in the phi direction on the surface itself, right? In other words, you change a parameter, you correspondingly change your position on the parameterized space. Likewise in the other direction. So you get these vectors and therefore these little pieces of area, and you can ask directly, well, how much does this little piece of area turn into on the parameterized surface? So if I have some little amount of area here in green, that's going to turn into some other amount of area on our surface there in blue. And in particular, you can compute that directly, and we're skipping those details in this quick reminder. But you can just see exactly what that stretching factor is, and it's right here in this equation, right? That shows this purple factor. That's what you multiply by green to get blue. So roughly speaking, if you want to do some sort of an accumulation argument, in other words, if you want to do some sort of an integral, not that we've defined that, right? But hypothetically, which is going to come up really soon, as in just a couple of minutes, if you want to chop up a surface into little pieces and do a chop it up, add it up argument, right, an accumulation argument, feel free to pull back through the parameterization and rewrite your integral in terms of your parameters. And in so doing, really the only thing you have to remember, other than obviously plugging in, is don't forget your stretching factor. And here it is. This is our formula for our stretching factor. Okay. All right. And with that noted, we talked last time about how this vector, the cross product, the vector whose magnitude is our stretching factor, keeping in mind, again, so there you go, same stretching factor. This vector that we're going to call capital N comes up in other places and in other ways, and it's actually really useful to have this as a vector as opposed to just a formula. So we're going to call that capital N, and that's going to be very convenient going forward. Okay, so this is about where we left off. Now let's actually do one of these accumulation arguments. I want to compute an area. How would I compute the area of the unit sphere? And of course, I know y'all already know what the answer is, right? And that's a formula y'all learned in high school geometry class. Right, but where did they get it from? Okay, you can. Turns out you can also make a clever single variable calculus argument for that as well. But let's forget all of that. Let's try to come at this in the sort of obvious, natural way of saying, hey, our sphere here, this unit sphere, is a surface. We can parameterize that surface, and we can use the techniques that we just talked about. So here's my parameterization. Now, let me pause as usual and point out, make sure you can do this. Where did I get this parameterization from? Right? So this comes from a spherical graph. The unit sphere, of course, is rho equals 1. And think about how you use the idea of a graph parameterization, spherical graph parameterization, of course. This is what you get for your resulting parameterization. Following the above formula, we take the partials with respect to those two parameters. We then take the cross product. You'll notice that I am skipping over a whole bunch of trig, right? And that's a little tedious, and it's a necessary evil. It has to be done. I think it'd be a great exercise. I encourage everybody to do this. Make sure you can follow through all these calculations, and it's just, I know you know trig, right? But make sure that your algebra and computational skills are such that you can comfortably slowly, I would imagine, but make sure you can get through this calculation. And here's what your capital N vector ends up being. Okay, now our stretching factor is the magnitude of that capital N vector that we just computed. That's another kind of tedious little calculation. Everybody needs to do this once in their lives. I've done mine. It's your turn now. Right? So compute the magnitude of that vector. The Pythagorean identity kicks in several times, very, very conveniently. And the nice answer ends up being that it's, wrong color. Nice answer ends up being that it's just sine phi. Very handy little result. Okay, with all of that done then, keeping in mind, we were going to try to compute the total area of the unit sphere. Well, the whole is the sum of the parts. Right, here's our first, this is our accumulation argument right here. The whole area is the sum of the little pieces of area. And now we have to ask, okay, well, yeah, but the little pieces of area on the surface are going to be some scaling of the little pieces of area in the pullback space. And reminder, we already know our stretching factor. Our stretching factor is the magnitude of capital N. And we've already computed that stretching factor, magnitude of capital N. So we can just plug that in. And what results then is actually a pretty easy integral to compute. Nice little double integral, nothing to it, plug and chug, answer. Familiar from high school geometry. Okay, everybody feeling good about that? Okay, so real quick summary. We actually kind of just did a real quick summary, so maybe I'll go super quickly through this quick summary. When you have a parameterization, that parameterization allows you to relate, moving through your parameter space with moving on your surface. And you can, as such, relate areas to areas, and there's the corresponding stretching factor. And we know the stretching factor is the magnitude of that vector, capital N. Now, I've separated it here as a unit normal vector times its own magnitude. This is going to be a convenient little breakdown. Now, nothing really important happened here. This is a direction, that's a magnitude, right? We've done this kind of thing before. Unit vector representing the direction, the magnitude representing the magnitude. The only thing that's really new here is while we have written previously this formula for capital N, we've never written it out in coordinates. Seems a little bit of a silly exercise to rewrite the whole thing in coordinates, having done which I can then crank out the cross product in coordinates. And if you do that, it turns out, seemingly coincidentally, that the coordinates of your capital N vector are two-dimensional change of variable stretching factors. And it's just kind of weird how that works out. It doesn't feel like we're doing a two-dimensional change of variables. Why would their stretching factors be relevant here? And it turns out there's actually a really good reason for this. We will kind of touch on what that reason is a little bit later, but ultimately we're not going to have time to go through exactly what's going on there. But of course, as always, if you're curious, ask me about it. I'll be very happy to discuss. Okay. All right. Okay. Now, here is a shortcut to a special case that happens sometimes. It's very nice. Special case. Good to have shortcuts identified when you can. This concerns in the case when you are looking at a graph, and furthermore, where you are choosing to use the graph parameterization, which of course is this. All right, so this being what a graph is. All right, this is the resulting graph parameterization. Okay. If you're using that parameterization, notice a lot of the calculation you can just go ahead and carry through. And so in particular, I can take my partials Just write it down. So we don't have to do that every time, as long as we're using the graph parameterization. You can take this cross product. It's always going to work out exactly like this, assuming you are using the graph parameterization. You can take the magnitude of that, again, assuming you're using the graph parameterization. And the magnitude, namely your stretching factor, namely the thing that we were going to have to go to the trouble of computing, it's always going to work out to be exactly this formula right here. So I encourage you to memorize this formula. Now, again, I cannot emphasize enough, this only makes any sense at all if you're using the graph parameterization. Right? This is a special case for that specific construction. But in that case, it's nice to save yourself some of the process there, and this is your answer. Now, having noticed that, there is another little bit of good fortune. You'll see that this little bit right there, that is magnitude squared of the gradient. Just happen to notice. And then furthermore, recall that the magnitude of the gradient is the steepness of the graph. Flashbacks to chapter 2. Right? So another little nice convenience that can be super handy sometimes, and I have an example in just a second. That stretching factor, again, when you're using the graph parameterization, applied, of course, to a graph, right? Your stretching factor is going to work out very conveniently as just this. So you don't even technically need to know the function f. All you need to know is how steep is the graph, and the area stretching factor is determined exclusively from that steepness. All right. So here's an example. This is a very real world, everyday life kind of a thing. So this came to me when my parents were putting a roof on their house several decades ago. But I put a roof on my house recently, and so very glad to have remembered this little trick that I'm about to show you. Hopefully you'll remember this next time you put a roof on your house. And roof tiles are expensive, as it turns out. And the labor of pounding them in, I mean, it's a tremendous amount of money to put a roof on a house. And very relevant to the price is what is the area. Right? And of course, you've got all these different faces on a roof of a house. Various different faces, and there are various different geometric shapes, parallelograms and trapezoids and triangles and etc. And I suppose one way you could compute that area is you could climb up onto your house and you could pull out a tape measure and you could measure all those lengths and then take that down and then do geometry for a long time and compute all of those areas one at a time and add them up. And I don't recommend that, not least of which because I don't want you to fall off the roof of your house and hurt yourself. Right? I'm certainly not going up there myself. So here's the much cleverer idea. And the idea is that our roof up here is a graph. This is the graph of a function, height as a function of where you are in the footprint. It's a graph. So we can use the graph construction. So we can use that shortcut we were just talking about. And the punchline then is that little pieces of area come from our stretching factor that we just derived times the little pieces of footprint area down here, dx dy. So the pieces of area on the graph, oh gosh, and this is going to be a weird one because it's on two different pieces. This amount of area up here is stretching factor times that amount of area down there. Now, so what? How does this help us? Well, it helps us as follows. It turns out most houses, not all, exceptions granted, right? Of course. This applied to my parents' house. It applies to my home. The steepness is approximately constant. You got all these different faces, and they're pointing different directions, etc. But they, for whatever reason, I'm not sure why, they always make sure. I think they call it the pitch of the roof. It's always the same on all of those faces. So the steepness is a constant. And if steepness is a constant, that means that this stretching factor is a constant. And constants will just factor right outside of the integral. What you're left then is you're adding up just a bunch of little pieces of area in the footprint, and therefore you just get the footprint area. And that footprint area, of course, is much easier and much safer to compute. Right? Just go around the perimeter of your house with a tape measure and a little quick diagram. Mostly rectangles. Super easy. Nothing to it. So you can turn a really hard geometry problem into a really easy geometry problem, and then you can accurately compute the surface area of your roof, and then accurately identify whether or not they're trying to pull a fast one on you when they're charging you for the roof. Does that make sense to everybody? All right, I think it's kind of fun when there's relatable real-world applications. Okay, moving along, off to section 7.2. Frankly, this 7.1 could be thought of as kind of we've already sort of segued into what we're doing here. We computed areas, which are really just a special case of computing an integral. And so, for example, if I have some surface here, and that's a two-dimensional thing, but I want to do some sort of an integral on it, and noting that it lives in a three-dimensional space, then I have a problem to address, and that is none of my integrals that we've developed so far in this course are really quite relevant to this. Right? I can't use a triple integral. Even though I'm in 3 dimensions, I can't use a triple integral because there's no volume. It's an area, it's a surface. I can't use a double integral, though, because double integrals happen in a plane, which this is clearly not. So, we don't have the right kind of integral. What I can say, though, and this is just recycling an old idea, there is still the concept of an accumulating quantity. And if the whole is, in fact, the sum of the parts, then on each little piece, we can answer the question, whatever the question is, and then we can just add that up over the entire surface to get the whole. Right? So, for example, let's suppose we're interested in, we have some surface here. We're trying to compute the amount of mass distributed over this surface here. Okay, well, the whole is the sum of the parts. And on any little piece of area, mass is going to be mass per unit area times area. Right? That'll give me the mass on each little piece. I add up all those pieces of mass. That gives me the total mass. Okay, maybe not mass. Maybe this is the side of a hill, and I want to measure how many blades of grass are growing on the side of the hill. Okay, well, yeah. So again, the whole is the sum of the parts. And on any given little piece, if I know number of blades of grass per unit area, multiply by area, that gives me blades of grass. And again, I add up over the whole. Right? So the whole is the sum of the parts, chop it up, add it up, just looks slightly different in this scenario because it's a new scenario. Right? Different geometric particulars. And the notation that we use here, again, this being a rip-off of old ideas, we're going to rip off old notations. Areas like so, adding up over the entire surface, as you might expect, like that. And thus we have ourselves a new notation for a new kind of integral. This is what we're going to call a scalar surface integral. Lots of things you can compute with a scalar surface integral. We've already kind of done one. We have computed a surface area. The whole is the sum of the parts, right? All of the area, that's the sum of all the little pieces of area. You get a little piece of area by multiplying delta S by 1. Double integral of 1 computes surface areas. That was the example we did on the previous page. How we doing? Okay, so a little bit of discussion of the terminology. I think surface integral makes sense because, after all, the domain is a surface. That's the whole idea. Why do we call this a scalar surface integral? Well, of course, you'll notice the differential is a scalar. You'll notice the integrand is a scalar. That's the justification we used when we were talking about line integrals, and we called it a scalar line integral. Here, for the same reasons, we call this a scalar surface integral. And by the way, just like with line integrals, there's another kind of surface integral coming. Remember, with line integrals, we eventually found vector line integrals. It came about naturally in a specific application. Right? Same story here. We're going to eventually find something called a vector surface integral. It's going to kind of naturally come out of trying to make an accumulation argument. It's just that it's going to be, orientation's going to matter, and we're going to have a dot product, and it's going to be more naturally written as vectors instead of as scalars. All right, but that's foreshadow. Okay, how do we compute these things? Good news, we already know. Because we've already talked about parametrizing a surface, right? And in doing such a parametrization, we've talked about how little pieces of area of the surface relate to little pieces of area in the pullback. And we've talked about how the stretching factor that comes from the parametrization is what does that for us. And that relates the input area to the output area. And again, we have previously written down this equation right here. ds is magnitude of n times ds dt, and thus this ds we rewrite like so, magnitude of n ds dt. So that's just kind of plugging in. Again, stuff we already worked out. We already laid all this groundwork in the previous section. So, yeah. So, formula. And now it's just plug and chug. Before I go on, pausing again. Questions? Everybody buying all of this? Okay. All right. Okay. Yeah, real quick, let me address a worry that you might be worried about. You look at this formula for computing the scalar surface integral, and you notice that the parametrization shows up prominently there. And of course, where did this capital N vector come from? Well, it comes from the parametrization as well. So there's a lot of stuff in this expression on the right that would appear to depend on the parameterization. You use a different parameterization, you're going to get a different capital N vector. You're going to, of course, have different formulas that you plug in for your x, y, and z. You're going to get a totally different integral. But that's not good. We're trying to compute something that's intrinsic to the surface. The parameterization shouldn't matter. How come our formula seems to depend on the parameterization, right? That's a legitimate worry. The good news is that even though you will get different integrals with different parameterizations, the value of the integral will be independent of the parameterization that you choose. And there's a significant amount of work that has to be done to establish that, but it does work out and it's fine. And if you want to read the book's presentation on that, you may. You don't need to. It's not really Math219 content. Okay. All right. But anyway, nothing to worry about. All righty. So let's see an example. We're going to look at the upper unit hemisphere. And there's going to be mass distributed across the upper unit hemisphere per this density formula right there. Now, real quick, keep in mind, density means different things in different contexts, right? Here we have, it says right here, mass is distributed on surface, right? That means mass is distributed over area. That means that this density is to be understood to mean mass per unit area, not per unit volume. There is no volume in this question. Is that cool? Is everybody happy? Right. Okay. And with that described, there's various things we want to compute. We can compute the total amount of mass. We can compute the location of the center of mass. We can compute the moment of inertia around the z-axis. Various different things you might reasonably want to compute. Okay. So how do we compute these things? Well, we're going to argue first that the whole is the sum of the parts. Right? Write it down as a surface integral. And then we're going to compute that surface integral by pulling back through a parameterization. Now, of course, in order to pull back through a parameterization, we're going to need a parameterization through which to pull back, right? So let's start with that. How are we going to parameterize our upper unit hemisphere? Well, again, this is easily written in spherical coordinates, right? Upper unit hemisphere, rho equals 1, right, for certain values of phi and theta. So rho equals 1, use the spherical graph parameterization. Here's your parameterization. Make sure you can do that, right? Starting with this parameterization, you can go through all of the tedious details of computing the stretching factor. We outlined that last time, and I think I hit that in my review real quick at the start of today. So anyway, again, make sure you can do that. There's various things to do. You have to compute the partials. You then take the cross product to get capital N. You then take the magnitude. Thankfully, a bunch of simplifications happen, and here's your result. Okay. And now we're in business. So let's do it. You'll notice, by the way, I have 4 separate calculations here. You're welcome and encouraged to wade through all of those. I'm just going to talk about the one because the pattern, I think, is highly consistent. You'll notice that as you read through the others. But here we go, looking at the mass calculation. Right here, first observation, the whole is the sum of the parts. That's how mass works. Mass is an accumulating quantity. On any given little piece, mass is mass per unit area times area. Right? Okay. So we have ourselves a scalar surface integral. Now, a couple things we already know. Here's our generic formula for how to compute ds through a pullback. Output area ds relates to input area d phi d theta by way of the stretching factor that we have established, magnitude capital N. Right, copying from previous page. Let's see here. By the way, we were just flat given that density was z. So we plug that in right there. Right, so pulling back through the parameterization turns our scalar surface integral into this iterated integral in the phi theta plane, and now it's just a matter of plug and chug. A couple of things to remember, though, before we do that. We did already compute our stretching factor. That was sine phi. Don't forget to plug that in. Right? And what is the deal with z here? And again, this is something that a lot of students kind of forget. Don't forget z comes from the parameterization itself. After all, the parameterization is literally telling us x, y, and z. Right? That's what a parameterization is. Position, x, y, z as functions of phi and theta, and so the third one here is z. So cosine phi. Everybody good? And yeah, at this point, it is absolutely purely plug and chug, and it's not even all that hard of a plug and chug integral. And you crank that out, and that computes the mass. So similar details. Well, similar big picture, different details in the other three examples. Okay. All right. Any questions about any of that? Okay, moving along. So here's where things get different. Now, just a quick reminder, we some time ago developed scalar line integrals, did several applications, and then we asked the question, how would we compute work? And things got weird. Orientation mattered. There were vectors where there should have been scalars. It's just different, right? And so we had to kind of come up with a new idea for a vector line integral because of looking into one physical application. So we're going to look into a different physical application this time. Of course, I missed the target again. We're going to remind ourselves of flux from Chapter 3. Now, everything I have circled here, this is all in Chapter 3. None of that's new. This is just a reminder. Remember, the big idea is that if you have a piece of surface, and if there is a flow of a fluid, and if you know what the velocity is, for example, and you want to determine the volume per unit time flowing through that surface, how do you compute volume per unit time? And we ended up with this handy-dandy little formula called flux. Now, do remember as well, there are different kinds of applications of flux. If, as we just presumed, your vector field represents velocity, then you get volume per unit time from that formula. But if, as is commonly the case, if your vector field is density times velocity, well, now you get mass per unit time flowing through your surface. Right? So make sure to keep these straight. If you happen to know right, what you're given, then make sure to interpret accordingly. Or said differently. Same idea, said backwards. Depending on which one of these you are interested in, right, design your vector field accordingly. All right. Now, as you may recall, this assumes that our vector field is constant. It assumes that our area is flat. All the calculations we did back in Chapter 3, we assumed those two things. The real world being what it is, stuff tends not to be flat. Stuff tends not to be constant. Right? How do we sort of generalize this idea of flux to a more realistic, non-constant vector field scenario? Right? Curved surface scenario. Again, that's how the real world tends to work. Now, how are we going to compute flux? Okay. Again, y'all can probably see this coming. What have we done with every kind of argument we've ever made concerning integrals? Was take your domain, chop it up into little pieces, and declare the whole to be the sum of the parts. Make sure that what it is that you're computing actually has that feature. Right? Not every quantity of interest is an accumulating quantity in that sense. But lots of things are, and so we're going to break up the problem into little pieces. On each little piece, we have an easy calculation. On each little piece, well, it's flat, and the vector field is approximately constant, and so on that little piece, nothing to it. On that little piece, F dot n times area, the area, of course, being ds. So nothing to it on the individual pieces. Everybody see where this is going so far? Okay, now I just glossed over an important detail. I'm sure you noticed. And that is that the surface here, we've got this surface, but if we're going to talk about flux, that means we're going to talk about the fluid flowing through the surface. Well, there's two different directions that fluid could flow through. Right? Fluid could flow through kind of what you might call generally upward, or it could flow through generally downward. Those are different. They're importantly different. You're going to get... we need to distinguish in practical, real-world scenarios. We need to distinguish between these two things. And the way we do that is with this thing called the orientation. The orientation being indicated by a vector that we call the orientation unit normal. So the orientation unit normal is just a unit vector perpendicular to the surface. There's two different choices, right? And pick whichever one points in the direction that you want to call positive flux. Right? So here, for no particular reason, I've drawn my orientation unit normals in what we might loosely call the upward direction. Right? The idea here is that for whatever reason, upward flux is the one that I want to call positive as opposed to negative. Given this arrangement, if the flow were downward, that would measure negative. Is that cool? Everybody happy? I emphasize there's nothing intrinsically positive about upward. This is arbitrary. Right? We just as well could have decided, for whatever reason, depending on the context, we could have decided downward was going to be our positive flux direction, in which case downward flow would be positive and upward would measure negative. So either one works. It just depends on how the question's phrased and what the asker intends. Okay. All right. And so with that noted, we're ready to start writing stuff down. Here it is. We've already agreed that on each little piece, the amount of flux that you get on each little piece is F dot N ds. That's from that little picture. Nice flat little piece of surface. Nice, presumably roughly constant vector field. So, old news. Adding that up over your entire surface to get your total flux, you just do the integral over the entire surface, and there's your formula for how to compute flux. Now, this is a little uncomfortable already. Let's look at this formula right there. Our differential is ds. That's a scalar. That's nice. That feels right. That's familiar. But now look at our integrand. Right? The orientation matters. This orientation is, again, kind of arbitrary. We get to choose whether to talk about it as being up or down. You don't get to choose when you're computing mass. Right? Mass is mass. You can't say, I'm going to choose to orient my mass upward. That doesn't make any sense. That's not a thing, physically, right? So this is intrinsically orientation dependent. So here's what I suggest we do. I want to flash back real quick to stuff that we wrote down when we were doing vector line integrals. And in particular, we were computing work. We argued that the whole was the sum of the parts. On any given little piece of our curve, work was force dot tangent vector ds. That's little s, distance, and I spaced that out weirdly. Let me fix that. There we go. And, of course, the other way to write that, arguably better way to write that, is f dot dx. Okay, so now, in fact, in the way we developed the work integral, we started with dx, and we subsequently rewrote that as TDS. In other words, dx was the natural thing. This is just displacement. Really natural. I was here, now I'm here. The displacement, right? That's a thing, right? We decided then to rewrite that as direction times magnitude. Direction being the unit tangent vector, that's the direction you're going. ds being the distance you're going in that direction, that's the magnitude. Okay. Well, look, we find ourselves in an analogous situation just with the chronology backwards. Look at what we got up here. We have a unit vector, just like we had a unit vector here, now in measuring or indicating a choice of direction through our surface, compared to t indicating a direction along our curve, but nevertheless an orientation times a size, right? And so kind of, if only by analogy, I think it makes loads of sense to pair these up together, just like these are paired up and naturally represented by dx. These, I'm going to kind of combine them together, represent them by ds vector. Not to be confused with the scalar ds by itself. ds vector includes the orientation. It includes that unit normal vector. So a really strong analogy. Right? Natural notational choice. Is that cool? Everybody happy? So having done that, now I think it's an easier pitch to explain why I would like to call this new construction here a vector surface integral. Surface, for obvious reasons, my domain is a surface. Well, yeah, of course, that's clear. But vector surface integral, because our differential is actually now a vector. Our integrand, we see now, more naturally written, is actually a vector. So thus the name vector surface integral. What do you think? Everybody good? All right. Good deal. All right. So how are we going to compute these things? Good news. We already have all the parts. We just have to kind of fit them together. So most of what I have on the page here is stuff we already know. There's really nothing new on the screen right now. All of this is previous development of various players involved in parametrizing a surface. Right, you got your pullback area, you got your corresponding surface, image area on the surface, and the various partials and the stretching factor, et cetera, et cetera. That's all old news. Here is just an absolute recopy of what we just were talking about. I'm just rewriting it down here for sort of visual convenience. Right? Notice, real quick, in ds, being our ds vector that we just discussed. So with all of that written down, let's sort of proceed, and let's see here. Well, we have this formula right here for the ds scalar. Let me sort of put that in there. There you go. Just plug it in for what that ds scalar is. All right, so hardly anything happened down to here. And now here's where you got to start being really careful. I'm going to notice something seemingly clear about this. Right? We have capital N that we just got from our ds formula, being multiplied by our unit normal vector little n, and well, again, direction, magnitude. Right? Direction times the magnitude, that's a vector. It's really tempting to say that this is capital N. And now I know y'all see this little star out here, right? I actually just committed a little math crime there. I did it on purpose, let the record show. I will reveal what the math crime was in a few minutes. For the moment, I don't want to get distracted with subtleties. They are important subtleties, and we will get to them, and they are a big deal, and they matter, etc. But for the moment, I just want to kind of get one in the win column. So let me just, again, I'm going to leave this as an asterisk. We're interested in computing vector surface integrals. We now, other than this asterisk, we now have a formula for how to compute a vector surface integral, aka a flux. Let's do one. So here we go. And again, I'll mea culpa later. Let's see here. We want to compute a flux right off the bat. There's our formula we're eventually going to plug into. We just derived f dot n ds dt. In order to be able to make sense out of that, of course, I have to parameterize our surface. Our surface is, you'll see here, well, it's part of this paraboloid. Right, flashbacks to chapter 2. This is a paraboloid. We want not the whole paraboloid, obviously, but we want just the part that's sitting above the unit square. So paraboloid, like this. Right? There's the unit square down here in the ST plane, the XY plane, unit square. And if I look above the unit square, there's going to be a certain amount of that paraboloid that'll just be sitting above that unit square. That's what I want to compute the flux through, and specifically the flux of this vector field. Okay, so off we go. Now we know we're going to need to parameterize. We are looking at a graph. So we use the graph parameterization. Very convenient. Right? When you have a graph, very often the graph parameterization is just the easiest way to go. We take the various partials. We take the cross product to get our capital N vector. Notice I don't need to compute any magnitude here, right? I mean, the formula, you can see right here, the formula I'm going to be plugging into for my flux. No magnitude required. Y'all may recall, same little bit of good news happened with vector line integrals. We didn't have to compute the magnitude of x prime. We just used the x prime vector. No magnitude needed explicitly. It's wrapped up inside. It's already there. No need to crank it out. So same good fortune here. So our N is like so. Let's see here. Now, there are some other details we have to worry about. Our vector field in particular, F, colors. Let me use this color. F is that. Now, of course, I realize that doesn't look like I copied that down right. What happened to the z's, x's, and y's, etc.? Well, don't forget, the parameterization tells you how to rewrite your x, y, and z in terms of s and t, or in terms of whatever your parameterizations are, or whatever your parameters are. So in particular, this z right here, right? I need to rewrite this z in terms of s and t's, because I'm going to be computing this in an st integral. How do I rewrite z in terms of s and t? Well, right here. There it is. Right? This, again, this is position. That is literally x, y, and z as functions of s and t. So z is this one, which therefore goes there. Everybody with me? All right, so that noted, likewise for x and y, there's your integral. It's a pretty straightforward integral at that. Polynomial, constant bounds, no problem. You can totally plug and chug that. Okay, and it looks like this is we'll end it a little early. Why not? I'm sure I owe you the time, and we'll call it right here at the end of this page and pick up here on Wednesday. See y'all later. Have a good one. Enjoy the eclipse. Keep those eyes safe.